Chapter 2 involved the concept of determinants, operations behind determinants, and how to use them in a few problems. So I'm going to start at the beginning. First, I have a 3 by 3 matrix that I'm going to find a signed elementary product for. And again, just to remind you, a determinant is defined as the sum of signed elementary products in a matrix. We're going to find the actual determinant in a couple of different ways, and then we're going to find the inverse. So I'm going to start with number 1. First of all, an elementary product itself involves elements in the matrix, none of which come from the same row or the same column. So for example, 5, 2, and 3 would be an example of an elementary product. Before I write down the actual product, I'm going to go ahead and talk about the sign. So this would be A sub 1, 1, A sub 2, 3, and A sub 3, 2. So to determine the sign, I write the rows in order, and then I look at the column indexes, which are 1, 3, and 2, and count the number of inversions that are necessary to put this back in order. The number of inversions is defined as the number of consecutive swaps that would put it together. So for example, if I swap 2 and 3, I would have 1, 2, and 3, and now the columns are in order. So this has 1 inversion. Now if it has an odd number of inversions, which is this case, this sign is going to be a negative number. So it's going to be negative 5 times 2 times 3. Let me do another example. So let's say instead I pick the numbers 8, 2, and 1. Those come from different columns and different rows. So that order would be A, row 1, column 2, A, row 2, column 3, and A, row 3, column 1. So again, the rows are in order, and I'm going to look at the number of inversions with the columns. So the columns are 2, 3, and 1. If I were to reverse these, this would be 2, 1, and 3. And then if I reverse these, it would be 1, 2, and 3. So this has 2 inversions. And an even number of inversions, I'm going to give a positive value to. So this one would be 8 times 2 times 1. Now, in general, an easier way to count the number of inversions would be the following. Let's say I have something like 5, 1, 4, 3, 2. What I do is I look at each number and count the ones after it that are less than that number. So starting with 5, I have 1, 2, 3, 4 numbers less than it. That would mean I would have to have 4 inversions to put 5 back in its place. Looking at 1, I don't have any. If I look at the number 4, I have 3 and 2. So plus 2 inversions for the number 4. And then 3, I have 1, so plus 1. So this would have a total of 7 inversions. And consequently, whatever product was generated from these elements would have a negative value. So that's an example of a signed elementary product. Now let's take a look at the determinant. So I'm going to rewrite my matrix, which was 5, 8, 4, 2, 2, 2, and 1, 3, 6. And I'm going to show 2 ways of finding the determinant. First, I'm going to show what's called cofactor expansion. So cofactor expansion is basically you pick any row in any column and create a set of minor entries and their corresponding cofactors. So let me start with row 1. What we're going to do is we're going to do 5 times the determinant of the matrix 2, 2, 3, and 6, which would be generated if I crossed out the row and the column that 5 is in. Then I'm going to do 8 times the generated matrix, which would be 2, 2, 1, 6. But I'm going to use a negative 1 here because that has a cofactor, or cofactor of negative 1. And then the last one would be 4 times 2, 2, 1, 3. So a couple of things that I want to review here. This matrix here is called the minor entry. So this one would be the minor entry if I took out row 1, column 1. This would be the minor entry if I took out row 1, column 2. And this would be the minor entry if I took out row 1, column 3. But we also have something called cofactors. Cofactors is where you incorporate the sign. So if I incorporate this sign, the cofactor for the middle one would be a negative value as a result. So cofactor by definition, C sub ij, is negative 1 to the I plus j times its corresponding minor entry. So in the first case, negative 1 to the 1 plus 1 is positive 1, and that's why you don't see a 1 here, and likewise you don't see a 1 here. So again, just to repeat, the minor entry is the actual determinant. The cofactor involves a plus or minus sign, and that basically, again, is to include the permutations and the inversions that are involved. So if I evaluate this using cofactor expansion, I'm going to have 5 times 12 minus 6 minus 8 times 12 minus 2 plus 4 times 6 minus 2. So 30 minus 80 plus 16, negative 50, this is going to be negative 34. And again, remember that I can get these using any row in any column. So let's say I were to use column 2 instead to calculate it. So using cofactor expansion, this would be 8 times negative 1 to the row 1 plus column 2, and its corresponding minor entry, 2216. Plus 2 times its cofactor, which would be negative 1 to the row 2, column 2, and its corresponding minor entry, which would be 5416. And then 3 times its cofactor entry, which would be negative 1 to the row 3, column 2, and its corresponding cofactor expansion, 5, 2, 4, and 2. So evaluating this, I would get 8 negative, 12 minus 2 is 10, plus 2 times positive 1, 30 minus 4 is 26, plus 3 times negative 1, 10 minus 8 is 2. Negative 80 plus 52 minus 6, so that is negative 28 minus 6, and again, negative 34. So the advantage here is that you can use any row in any column, and therefore obviously it would be ideal to pick one that has a lot of zeros in it, fewer minor entries to work with. So that's one method. Now I'm going to rewrite the matrix and show another method. So 5, 8, 4, 2, 2, 2, and 1, 3, 6. And another way to calculate a determinant would be to use row operations. And the idea of row operations is, again, to get a lot of zeros in there. You can even get it into an upper triangular matrix. If you do so, all you need to do is multiply the diagonal elements together. So I'm going to try to illustrate some of the row operations here. Let's start with the row swap. So if you swap a row, 2 rows, that changes the determinant to its opposite value. So if I swap row 1 and 2, this is going to become negative 2, 2, 2, 5, 8, 4, 1, 3, 6. Another property is that you can factor out a number from a single row, and that becomes a multiplier. So if I factor out the 2, this becomes negative 2, 1, 1, 1, 5, 8, 4, 1, 3, 6. The third operation we have, and these are all mimicking our row operations from chapter 1, is that if you add a multiple of one row to another row, that actually does not change the determinant. So here I'm going to take row 2 minus 5 row 1s, and here I'm going to do row 3 minus row 2. So negative 2, 1, 1, 1. Row 2 minus 5 row 1s is 0. 8 minus 5 is 3. 4 minus 5 is negative 1. 1 minus 1 is 0. 3 minus 1 is 2. 6 minus 1 is 5. And I'm going to keep doing some row operations here. So for example, this would be row 3 minus 2/3 row 2. And again, that doesn't affect the determinant. So I have negative 2, 1, 1, 1, 0, 3, negative 1, 0, 0, 5 plus 2/3, And now I have it as the upper triangular matrix. So all I need to do is multiply the diagonal elements to get the determinant. So negative 2 times 1 times 3 times 17 thirds, negative 34. Okay, I think I found the determinant enough different ways. So let's talk about the inverse. Last time I'll write this matrix, promise. 5, 8, 4, 2, 2, 2, 1, 3, 6. So one way we learned about calculating the inverse, and it works best with a 3 by 3 matrix, is that A inverse equals 1 over the determinant of A times what's called the adjoint of A. Well, we already know the determinant of A, obviously. We did it 3 times. So now I want to focus on the adjoint of A. To do the adjoint of A, this is equal to the matrix of cofactors. So C11, C12, C13, C21, C22, C23, C31, C32, and C33. But the adjoint is the matrix of cofactors transposed. So what I'm going to do is I'm going to fill in all my cofactors. So each time I'm going to cross out a row and a column and calculate the corresponding cofactor. For example, for cofactor 1, 1, we'll be crossing out row 1, column 1, calculating that determinant, which would be 12 minus 6. So that would be 6. Incorporating the plus or minus sign, so negative 1 to the 1 plus 1 is positive 1, so we're set there. Cofactor 1, 2 would be crossing out row 1, column 2. So 12 minus, oops, that was a 1. 12 minus 2, which is 10. But since this is a cofactor, I need to include the plus or minus 1. So that would be a negative 10. So putting in the rest of the numbers, I would have a 4, a negative 36, a 26, negative 7, 8, negative 2, and negative 6. And that I need to transpose. So let me do this double check. Negative 36, that came from 48 minus 12, which is 36, and then a negative for the cofactor. So A inverse is 1 over the determinant of A, which I've done many, many times, 1 over negative 34, times the matrix of cofactors transposed. So 6, negative 36, 8, negative 10, 26, negative 2, 4, negative 7, and negative 6. And that is our A inverse. Now, obviously, you can do it the way we learned in Chapter 1, setting up the identity matrix doing row operations, which is ideal if you have a 4 by 4 because the determinant gets harder to find. But if you feel comfortable with this way, it's a faster way of finding the 3 by 3 inverse without having to go through row operations. Now let's look at a couple of things involving the properties of matrices. For example, over on the right-hand side, I have a matrix A, and the question is, what values of x make A squared singular? Well, if a matrix is singular, the determinant would have to equal 0. So basically, I want to solve when the determinant of A squared equals 0. But the determinant of A squared is the same as the determinant of A times the determinant of A. Oh, actually, let me back up a step. The determinant of A squared is the determinant of A times A. And we had the property that the determinant of a product of matrices is the same as the product of each individual determinant. So this is the same as the determinant of A times the determinant of A. So basically, all I need to do is find when the determinant of A squared equals 0, or i.e. the determinant of A equals 0. And I'm going to use my cofactor technique because I want to take advantage of the fact that I have all these zeros in the middle. So expanding along the middle row, I'm going to have 0 times a matrix, which I really don't care about, plus x times a matrix x minus 1, 3, negative 1, and x minus 5, plus 0 times another matrix, and that has to equal 0. Now let me check my cofactors. So this would be 0, this would be negative 1 to the 4th, so that's positive, and then 0. So multiplying this out, I would have x times the quantity x minus 1, x minus 5, plus 3 equals 0. X squared minus 6x plus 8 equals 0. So x minus 2, x minus 4 equals 0. So it is singular if x equals 0, 2, or 4. Alright, so again, I'll use some properties of matrices. Let's say I have a matrix. Don't know how many dimensions, but I know that the determinant is equal to 7. Now I want to calculate the determinant of 5A transpose. Well, to review a couple of the properties, I know that the determinant of A transpose is equal to the determinant of A. But I have 5 times A transpose, and I don't know how many rows, so technically I have 5 rows that got multiplied by, or I'm sorry, I have n rows that got multiplied by 5. So the determinant of 5A transpose is equal to 5 to the n, because I have to factor a 5 out of each of the n rows, times the determinant of A transpose. So the final answer is 5 to the n times 7. Now, let's use that same idea here. So, the determinant of 3A, all of that inversed. The determinant of A inverse is 1 over the determinant of A. But each of these matrices got multiplied by, or each of these rows got multiplied by 3. So the determinant of 3A to the inverse, actually I could do this first. That would be the same as 1/3 A inverse. So that's going to be 1/3 to the n times 1 over the determinant of A. And so 1/3 to the n times 1/7. Now the last one. So the determinant of A squared minus 2A. So I could factor out an A and make this A minus 2I. So that would be the determinant of A times the determinant of A minus 2I. The determinant of A is 7. Now the determinant of A minus 2I, that is not equal to the determinant of A minus the determinant of 2I. So there's no way I can figure this out, which means there is not enough information. Now let's start looking at some problems. So we talked about eigenvalues and eigenvectors in chapter 2, and that's what I'm going to work on here. Just to review, an eigenvalue and an eigenvector basically has the following property. If I take b times my eigenvector x, the result is a scalar multiple of x, and these two are identical. So if x is 1, 3, the result is a scalar multiple of 1, 3. To calculate this, what we did was we rewrote this as bx minus lambda x equal to 0. Factored this into b minus lambda I x equal to 0. And since we're looking for a solution that's not trivial, I want to make sure that b minus lambda I is singular, so that I have an infinite number of solutions, which means that the determinant of b minus lambda I has to equal 0. So putting that all into place, basically what I want to do is make sure that the determinant of negative 10 minus lambda, 12, negative 8, and 10 minus lambda has a determinant of 0. Multiplying this out, I have negative 10 minus lambda, 10 minus lambda, plus 96 equals 0. Now, before I forget, some vocabulary. This entire thing on the left side, is called the characteristic polynomial. And the entire thing, including the equal sign, is called a characteristic equation. And since I'm on the topic of vocabulary, let me just add that x is your eigenvector and lambda is your eigenvalue. Alright, so now I'm going to finish solving this. So if I multiply this out, I'm going to have negative 100 plus lambda, 10 lambda, minus 10 lambda, plus lambda squared, plus 96 equals 0. So lambda squared has to equal 4. Lambda equals plus or minus 2. So first you find the eigenvalues, and then you find the eigenvectors that correspond with it. Let's start with lambda equals 2. So going back to my equation, b minus lambda I x equals 0. I'm now going to substitute in 2 for lambda. If I substitute in 2 for lambda, I'm going to end up with negative 10 minus 2, 12, negative 8, and 10 minus 2. My vector x equal to 0. So I guess technically this is a 0 vector. Setting this up as a augmented matrix, this would be negative 12, 12, negative 8, and 8, 0, 0. So if I do some row operations on this, for example, I could divide this by negative 8, this by negative 12. I'm going to have negative 8 and negative 12. I'm going to have 1, negative 1, 0. 1, negative 1, 0. I'll do row 2 minus row 1. And I'll have 1, negative 1, 0, 0, 0, 0. So rewriting this as equations, this means that x1 minus x2 equals 0. x1 equals x2. So if my solution vector is x1 and x2, x1 equals x2. Factor out the x2, and I have 1, 1, x2. So for lambda equals 2, my eigenvector is 1, 1. And it could be any scalar multiple of 1, 1. So if you want to add the t to indicate that it can be any scalar multiple, or we can just leave it 1, 1 for the eigenvector. You can think of it as the principal eigenvector. So similarly, let's do lambda equals negative 2. If I do lambda equals negative 2, I'm going to have negative 10 minus negative 2, so that becomes plus 2, 12, negative 8, 10 minus negative 2, or 10 plus 2, augmented with 0, 0. So again, doing my row operations, this is going to be negative 8, 12, 0, negative 8, 12, 0. I'll do row 2 minus row 1, and I'll do row 1, let's see, divided by negative 8. So the result will be 1, negative 3 halves, 0, 0, 0. So again, translating this back into an equation, this means that x1 minus 3 halves x2 equals 0. x1 equals 3 halves x2. So if I were to write my solution vector, x1, x2, it would equal 3 halves x2, because x1 equals 3 halves x2, x2, or 3 halves 1, x2. So if lambda equals negative 2, the corresponding eigenvector is 3 halves 1, or any scalar multiple of that. And there's my eigenvalue-eigenvector problem. When we get on to later chapters, we also will look at 3x3s, but for now, just stick with the 2x2. Okay, of course, I have to add some proofs with each chapter, so that's what I'm going to do here. we're going to prove that if the determinant of A equals 0, then the rows of matrix of A are linear combinations of each other. Now remember, there are different kinds of proofs. Some of them you actually do math on. Some of them you're just sort of explaining based on the concepts that you have with the material that's involved. So if the determinant of A equals 0, let's start there. So I'll do this. Okay. So if A equals 0, that means row operation on A created an upper triangular matrix with a row of zeros. Because if I do row operations on this and I have a row of zeros somewhere, then I know that the determinant has to equal 0 because the determinant is the product of the diagonal elements. But row operations are generated from multiplying or adding combinations of rows to each other. So, if the determinant of A equals 0, then the rows of A must be linear combinations of each other. Second proof. Let A be a 3 by 3 skew symmetric. Prove that A plus I is invertible. So skew symmetric, just to review, means that A transpose equals negative A. Now if A transpose equals negative A, what that means is that my diagonal elements are 0 and everything else are the opposite of each other. So I can actually put a skew symmetric matrix together that looks something like this. 0, 0, 0 along the diagonals. A, B, C, negative A, negative B, and negative C. So if I were to take A plus I, this would equal 1AB, negative A, 1C, negative B, negative C, and 1. Now I want to prove that this is invertible, so I want to look at the determinant, 1AB, negative A, 1C, negative B, negative C, and 1, and take the determinant of that. If I take the determinant of that, I get 1 times 1 plus B squared minus A times negative A plus BC plus B times AC plus B. And simplifying this, I get 1 plus C squared plus A squared minus ABC plus ABC plus B squared. These cancel out, and I get 1 plus A squared plus B squared plus C squared, which notice no matter what the value of A, B, C I put in is never equal to 0, and therefore it's invertible. Okay, last problem I want to do is Cramer's rule. So Cramer's rule was a way to use determinants to solve for each of the components. Basically, in x sub I is equal to the determinant of A sub I over the determinant of A. And the determinant of A sub I is basically the matrix involving the coefficients, but with the ith column replaced with the right-hand side values. And then the determinant of A would be equal to the normal thing. So in this case, x sub 2 would equal the determinant of 5, 3, 1 Now, instead of putting in 2, 2, 4, I'm going to replace it with 8, 5, and 3, and then 1, 0, and negative 2. Over the denominator, which is 5, 3, 1, 2, 2, 4, and 1, 0, negative 2. So that's how you would calculate x sub 2. As another example, I'll do x sub 3. So x sub 3 would be 5, 3, 1, 2, 2, 4. And this time the x3 values will be replaced with 8, 5, 3. All over 5, 3, 1, 2, 2, 4, and 1, 0, negative 2. Good luck studying for the quiz.